Right, so we're good for the second seminar session. Okay.
Okay, thanks. So let me start with a recap of what we explained last time. Last time we saw the objects, which are circuit, and random restrictions. And then we saw that certain hard function, which is a parity function, cannot be computed by small size samples. Yeah. So the main thing doing this is the half function. We saw a bucket and a couple of buckets, one in the lower bound and another in the correlation bound. So what you see a proof of Hastad is attributed to Rasto. I don't know how much of what I will be talking about is the original proof. So yeah, so there is an exposition due to for being in a nice primer called switching lemma. And what I will be presenting is not it's not from here as well. I mean, the current presentation got refined, and I think probably now in a more simpler form. Yeah, so we'll look at Rathbrough's proof of Hastad switching lemma. Then another switching, and finally we'll see another switching lemma due to Rossman, which is the Entropic Switching lemma. I will define a statement.
The board, you press the light switch, which I do that one. The light switch, yeah, I think that's or that's not a light switch. Yes.
Let's see. Let's first finish this and then see what happens. Okay. Okay. Let's recall the technique of switching lemma from last time. Suppose you have a L, which is a pt.2 formula of width learning. And let's see what P random restriction is. P random restriction sets each bit independently to 0 with probability 1 minus 2 by 2, 1 with probability 1 minus 2. Leaves it unset with probability. This is a P random restriction. Yeah, so if you apply a P random restriction to a depth 2 formula, decision will be there. Becomes small with head. Or another way of saying it is the probability that it has large instantaneous after random restriction is none. This is a statement of Hastad switching lemma from last time. We are going to see a different proof of this. This is the encoding proof. Yeah. What this statement is saying is that the best decision tree for f restricted to rho is small with high probability. So instead, what we'll be doing is the following. We will define a canonical decision tree. This is a specific way of defining the decision tree. Define a canonical decision tree. So this canonical decision tree is defined. So given these are the inputs for the algorithm which constructs the canonical decision tree. It takes as input depth formula. For now, let's assume it's a CNN and a restriction, and it spits out the decision. Okay. Yeah, so I'll define what is how this algorithm for constructing canonical decision trees. But yeah, so what we'll be doing is that the depth of a canonical decision tree is small with high probability. This is saying that the best decision tree is small. This is saying that even the canonical decision tree is small. If you can show that the canonical decision tree is small, that implies that the best decision tree is small. Right? So we'll be doing this, and this would imply F is what? F is a DNA. The depth formula. Let's go.
Okay, but so you say that this probability is small for every F.
Yes. Yeah.
For every F that has a DNF.
For every F
of width W. Of width W. Right. Oh, right stuff. Depends on
it's just this lemma with this statement replaced by that.
You're saying in general, the canonical decision trees could be higher or deeper than the best possible decision tree, but you're saying that even with high probability, this canonical one is going to be small. Even this canonical one is going to be small, so it's the best one.
So I think is there any confusion?
So what is I'm going to
I haven't defined yet. I'll define. Yeah, so now I describe an algorithm given a so you're given a F, which is an of cost. How do you consider a decision tree for this? Given a restriction. So first step is you scan the okay. I'm assuming this is the representation. I mean, this formula is also this is also the same formula, but I am assuming that this order is fixed. So the in some sense, it's not just working with the function, it's just working with the tree. the input.
So you're saying you're not just given the function, you're actually given a particular formula for the function.
Yeah.
So, which is a bit strange. It shouldn't really be called canonical, I would say, but fine. Because if it were canonical, somehow it shouldn't depend on them. But fine. So, okay, so you're given a particular formula for this function f.
Yeah. So the form algorithm assumes this tree representation. If you interchange the C1 and C2, the function will be the same, but the algorithm will output something different. Yeah, I don't know find the leftmost closest like that. CL1 respect to the row is
Not wrong.
not. Okay. Yeah, that just means that CL1 use cancel and find the first clause which doesn't get simplified by row. So you pick that. Say you look at the variables in tier 1. Star variables. By star variables, I mean we are working with a restriction. That restriction must affect some variables in L1. Q is a set of star variables, unset variables.
Could be. Could be.
No, it will not be.
Well, it might because all the variables have been set to 0.
Yeah. So construct this complete distinct construct QM, which is this complete distinct tree by querying all the variables in it. Right. So typically, if you have a or, what is the decision tree for it? If you have x1 or x2 or x3, so what is the most natural decision tree for it? You query x1, x1 is 0, you query x2, x2 is 0, you query x3, all they are 0, you are 0. If any of them is 1, you are provide. This is kind of the best decision tree for this. This is not what we're putting here. What we will do is we'll put the complete different.
So you query all the variables, even if they fix this particular clause.
Yeah. There's essentially only one 0 part here. Every other thing is a 1. This seems like a redundant. This is a redundant thing.
No, but it might kill other clauses, I guess is the point.
Sorry?
It might kill other clauses. Like if you've learned, right? Maybe you didn't need to learn x3 if you know that x2 is 1, but if you do, then that might kill other clauses.
Yeah.
Which I guess is
Construct T1, which is complete binary tree on variables in things. And for this, we alpha of this one attached PDQ of F plus equal to alpha. Okay. Okay. And this is a smaller formula, and there is an algorithm here. Okay, let's go over it again. We have a CM, which is like this. You are given a restriction and you want to construct a canonical relation. What you will do is scan from the left, find the first clause which is not becoming one. Take that clause. Let's say Q1 is a set of variables. You make a complete binary tree of that. And once you make Q1 at each v, suppose say this v is alpha, or this gives you a restriction, right? For example, this path it is setting x1 to 0, x2 to 0, x3 to 0. Okay? That gives you a restriction. So now you construct the decision tree of this CNF and then attach it to that. So that is a procedure using which you can construct a canonical relation. And now we'll be trying to show that the canonical relation tree constructed in this manner will be small with height forward. Okay. I hope the definition of canonical relation tree is clear. So I'll leave this for a while. We'll be referring to this again and again. Now let's make some simplifying assumptions. So we set out to show that the canonical relation depth of F restricted to rho. We're interested in this problem, right? We're interested in the probability that the canonical relation tree has depth greater than t. Instead, it's enough to work with this guy. We have a bound on this. If you are able to show, if you are able to bound this, it's same as bounding this. You see why?
Bounding it in with like an exponent.
Yeah, so let me just say is that then some constant for some other constant rather constant. Sorry?
Why do not 5?
Maybe not 5. Fine, yeah, this 5 is an illusion.
Because of some geometric sum?
Yeah, exactly. So the moment you have a bound of this, right, we can sum this up for u greater than t. Which will essentially be the leading term. Which will be some constant times I mean, since this is the term. So it's enough to work with the property that definitely that was T. So, okay, let's unpack what it means to say that the canonical relationship has that T. Okay, we have an algorithm of canonical relationship. What does it mean to say that the canonical relationship has that T? Okay, suppose the canonical relationship has that T. The canonical relationship probably looks like this. There is an initial segment which came from class CL1, and then yeah, so this is the long part from the canonical relationship of this is what T. There is an initial segment which came from class CL1, then another which came from CL2, another class, and so on. So there are a bunch of clauses where the canonical relationship must have picked variables. Right? CL1 is the first clause where canonical algorithm picked variables and so on. Yeah, firstly, yeah, canonical relationship has that P. There must be some R clauses. CL1 to CLR, which got involved in the construction from this one.
Yeah, only
along this long path. If you take a different formula, not guaranteed. If you take a different path, nobody knows what happens. Let's say let's call these branches or these restrictions as I1 are the restrictions along this long. Okay. So another thing to note is suppose you have this clause. As we have seen here, there's only one zero path. If you try to construct a canonical relationship from this, or complete identity of this, right? You'll see that there's only one. I might have ordered it, but you'll see that there's only one zero path in this, which is exactly the path that sets all of them. All the results will be x3 to 1. This is the only restriction of these variables, setting of these variables, which makes this clause real. And furthermore, we are not attaching any for each values. My bad. In the construction of canonical decision tree, it doesn't make any sense to suppose we found a complete binary tree of the variables here. right? There are several 1 paths in this and 1 0 path. It doesn't make any sense to attach anything down here because by here itself, the formula is becoming 0.
Oh, I think because this 4 is 0, so the and is 0, so the formula is 0. So at that point, you already know the formula. 0 left. Okay. So then you don't make the number 0.
Yeah. So you don't attach anything to the 0 path. You only extend the 1 path. Okay. Suppose there is a path of length t in the resolution tree. It could be broken into these paths like that. There's only 1 0 path. Right. This is not it. Let's call the 0 path in this sigma 1. The first chunk as sigma 1. The second chunk as sigma 2.
You're saying that you can choose your long path while avoiding all the 0 path because there's certainly always at least one as long, at least as long. Right?
Long path would not have gone along this sigma.
Maybe in the last layer.
Maybe in the last one it might have.
But we could also choose some other one.
Yeah.
And it will have the same thing.
Okay. Right. Yeah. Yeah. Okay. If the canonical relation are empty, bunch of things happen. There are R clauses which are attached, and each clause must have assignments to one function of variable. That's all setting. In CL, some of the variables are set by row, and some of the variables are left star by row, and those are set by row. So there is a subset Q1, which is subset of variables of CL1. Yeah, this is the same one from the algorithm. This is the same Q1 from the algorithm. Yeah. If there's a long path, a bunch of these guys, you'll be able to find a bunch of these guys. Right. So now what are we interested in? Okay, just keep it on the side. We'll come back to that.
Yeah.
Sorry.
What do you say? Yeah.
Okay. I haven't written anything. Okay. So, as respected to row, if you extend row, first we know that the variables in phi 1 are the star variables only. These are not set by one, right? If these variables are set by row, our algorithm wouldn't have to validate, right? So this is just maybe bad notation, but it's just notation which are using. Okay, that this is just extending this restriction with this restriction. These two are on disjoint. These two are setting disjoint. F respect to row with row extended over sigma 1. And furthermore, the first clause which becomes 0 on the restriction will be here. Everything before is becomes 1 according to row. Setting more variables is not going to change that. So the first clause which becomes 0 by this restriction is here.
Okay. By first you mean left clause.
Left hand clause.
First clause becomes.
And we'll f is equal to I1 extended with sigma, you see, which is same as saying this is the zero path. F is rho extended with sigma 1 and sigma 2. We don't know anything about it. But what we can say is if you go along phi 1 and take sigma 2, then this becomes again 0. And PL2, which is the second clause which is picked by Prahladh, is the will be the first guy to become 0 on this restriction.
On F restricted to row composed with I1.
Yeah.
Go on.
And so on. Now let's define some restrictions. Let's call some restrictions bad. So what is the bad restriction? Bad restriction is a restriction rho such that CBT delta of F rho and what we're interested in this language is the probability that what is the mass of the bad. So here's where the encoding part comes in. So the way we're going to do it is we're going to define the encoding. For a file which maps bad description will set up all restrictions. Okay. So how are we going to define this encoding map? Suppose there is a bad restriction code. By a unpacking statement, they must have existed from sigma 1 to sigma r. There must have something. There must have been some r, and there must have been some sigma 1 to sigma r. You just map it to it's bad. There would have been some sigma 1 to sigma r, and you append it. And you know that you are setting 3 more variables. So let's first see one thing. So what is the probability mass of rho compared to probability mass of PL? So there are some P stars here, P variables which are stars here are being are becoming zeros or ones. So I claim.
So by probability mass, you mean the probability of sampling a uniform row versus the probability of.
So this is the point in the sum space and the mass you are getting.
You're asking for that. What's the probability of that fixed point?
Yeah. What is the probability of
You're fixing a row in the answer. Like,
what is the probability of getting this particular row in the sample?
You mean if I choose a uniform row, like
You choose according to RP.
according to our class. Okay.
So there are some t variables which were stored here, and they were set to in a particular variables.
Wait, what's this probability? My row is the probability that I choose.
Let's solve the restriction prime.
Prime. So that's the probability that I choose row prime if I sample according to our p. So is that it?
Correct.
Now you're saying that the only difference is that these t variables that were free in row, and then have to probability row to the t times something, they are now set in row prime. So, and that happens with that probability times something. Yes.
So this is the relationship between these two guys. So here is this mark was the one. Okay. No two bad restrictions are going to the same encoding. Are encoded to the same value. Suppose
it will 1-to-1.
Yeah. Suppose this is a 1-to-1. Then now what would you do? What is an upper bound on property? Oh, this is an upper bound. So wow.
If they were 1-to-1.
Yeah, this is one. Suppose if it's many to one. And you know what this, you have a bound on this degree. Right. Let's say it's B. Right. So what would this be?
Must be.
Right. So now we are the rest of the proof is going to involve bounding. Given a row prime, how many rows led to that? Right. For the rest of the proof, we are trying to we'll start with the row prime and try to extract the possible rows which could have led to this one.
No, to say that E is rather small.
Sorry?
Small.
Yeah. So, yeah, we want to see what B is like. So let me say this a bit more formally. And the definition of the canonical there should be fine. Can I rest?
Another way of saying it is that like the image of phi has to be smaller, right? Right. Right. Just by that difference in probability.
I don't think we are exploiting that as much. The image is small.
I'm trying to understand what are you encoding? Because you call it an encoding argument. Isn't it like you want to encode a guy from bad using a guy from all and the specification of which neighbor you are?
Okay.
Is that some kind of, do you get some kind of encoding like that?
I mean, maybe in the encoding, the word is used because each edge will be given an encoding. The way you give a bound on this is by encoding the edges.
Okay. Oh, I see. All right.
Okay, I'll probably erase the canonical relation tree. Again, let's recap before erasing it. How are you constructing canonical relation tree? So you are given a depth formula of this kind. You scan from the left. Then look up which is the control. Find the first clause, which is which doesn't become 1. Right? Take that and make complete relation tree of it. And at each one leaf, you recurse. And
yes, yeah, there's lemma is also PMM, but some limitation of
sorry, what is it?
So this no. S, there's no S. That's actually a row. I think.
Oh, which?
S now.
This one.
That's a row.
F is PNF and rho is a resection.
There's no permutations. So it's just so sigma 1 to sigma r, or you choose the variables that were selected by this algorithm and you set them all to 0. Can I understand that correctly?
Right. Yes. Set all of the literals to 0. So sigma 1 is the assignment which sets the literals to 0.
Right, and there must be some way. I mean, you select, right? So this algorithm produces the decision tree. You choose and we're trying to, let's suppose that this decision tree has depth t. Now take the leftmost path of depth t in this decision tree. Right, we've drawn it there. Along this path, there are some variables that are queried. Sigma 1 sets the first block of these variables to 0, sigma 2 sets the second block, and so on. And in the last level, sigma r sets the last variables to 0. Now you're considering this map, which takes a permutation, which takes a restriction rho and maps it to the restriction rho prime, which additionally, besides all the variables that were set by rho, sets all of the sigmas to 0.
And yeah, probability of all is what?
1.
And okay, what can be? Can be equal to 1 divided by 2?
Sorry? How large is P? Yeah. It's assume it's close to 0. I mean, bounded at half. At most 1. Yeah.
I mean, P is close to 1 by 2.
Yeah, that's your problem. No, but think of P as being at most 1/100. Because last time, when we proved these lower bounds, P was never bigger than 1/100. Right? When we proved these lower bounds on the sides.
We do not assume about P.
Which the statement which I have written, I didn't assume.
We have known that P is small.
Yeah, I have mentioned that, but yeah, I have. It needs to be there.
Less than half is enough.
Less than half is enough. So where are we so far? So we defined this encoding map, which is mapping bad restrictions to all restrictions in the map. And we said this is a Melligon map, -1, and you want to see what is the pre-image of a given profile. How large can it be?
Is there anything you can tell us why we should have an intuition where it should be small?
Why the pre-image should be small? Fine. Small is again relative, right? I would be showing that the pre-image is rather than roughly width to the t. Yeah, I think the proof will have the intuition. Yeah, okay. So I just added the canon condition for. Yeah, then maybe here and then maybe even a slightly different way of looking at this. So what is this probability applied? It's just the sum of, look at this bad head. And sum of all the masses of elements in this. Which is same as by this. Right. Yeah, I'll do some simple pushing for one or two steps and then arrive at something which is maybe.
No, there should be some.
Yeah, it's a pattern of. So this can be written as low prime. We'll do this. Instead of going over this, going over left, all the restrictions here, and summing up the corresponding phi of rows, what we're going is looking at the image and taking the mass, and then asking how many of the rows correspond to the.
You're using the fact that every three images fixes the same number of stars, zeros, and ones.
So differently, this can be thought of as expected pre-image of you sample a random restriction and ask what is the expected pre-image according to this.
Wait. Oh, true. Okay. Yeah, fair enough. Because it is 0 and
yeah, this way of looking at it is something. Yeah, is something which I think we know that I think there's some work with Prahladh, Shankar, and stuff. And the nice thing about this is it unifies both Rasbrough's group and the Rossman group. Till this point, both the groups do this. Okay. Just that in the Rasbrough's group, we are putting a worst case bound on the expectation. I mean, there are two ways of bounding the expectation. I mean, if you have a uniform compound in this set,
what do you mean?
I know. For every row, P inverse row is upper bounded by something.
The worst case.
Worst case bound, yeah.
Or
worst
can you
case
get
bound,
transfer?
you get transfer. You get an average case bound, you get off.
I see, but then if you do like the size, log, what, something, one here, now there's now you get an entropic thing. Okay.
Yeah, so in that sense, Rossman's proof is slightly clever.
Okay, so you're saying Rasgorov is the worst case bound, is it? So it just said that every pre-image is ever bounded by a source.
That we got. Or some 100 5.
Okay, and then Rossman just looks at this particular average.
Yeah.
And can bound the average slightly higher. Okay.
I mean, you'll not be able to compare the final statements of the both switching lemmas. They are incomparable, but
okay. Good. Now we're going to show us an upper bound on all of these images.
let's look at the worst case bound. So, suppose I gave you P of rho, these subsets Q1 to QR, and phi1 to phi. Can you recover?
Oh, wait. Yeah, of course. Yeah. Right.
Yeah.
So we have to figure out.
So Q1 and QR does not specify the clause. It just says.
It just gives you a okay. How am I specifying these again? Yeah.
You can even specify them without referencing to the ball.
Yeah.
Without referring the variables.
You mentioned which clause you're taking it from.
You don't have to. Yeah, it's not from this.
Yeah. So if someone gave me P of rho and told me the variables x1 because x1 is yeah, told me the names of the variables, then we will do it like that. But instead, you could also exploit that as just a DNF. I mean, it's not a there is some structure to the DNF, and so the positions of these variables can be efficiently mentioned.
Isn't that what you're doing by encoding this?
Right.
What
You
we-
can just say T log W bits. By specifying T log W bits, you would have specified these Q1 to Q2.
But that's roughly what is right. That's I mean, the dumb thing would be
There
to
would be
use,
some
the dumb thing would be to use T log n, right? But now you can do it using T log W,
yeah,
right? By being smart.
Right. Yes. Yeah. If you were to specify T variables would need P log n bits, but these variables are coming from a DNF, and these are not.
You know what, right? So you know which. Well, the point is that. So you know which clause is C1, and you know that Q1 is a subset of the variables in C1, and there's at most W variables in C1. So you can specify Q1 by telling me which variables in the first clause belong to Q1, and that's those many possibilities and so on. But now, okay, so but now for pi1, you just specify it's binary because now you know Q1, so all you need to specify is how to set it.
Yeah, so
And once you know both pi1 and Q1, you actually know what clause is CL2. Okay. Oh, yes, I agree. And so on. And you keep going down the tree. And this will specify. Yes.
yeah, so the claim is that given I sphere of rho and
Oh, that's it.
T log W plus T bits,
Oh,
you'll be able to uniquely recover rho.
right. So there's at most.
So the pre-image is
W times 2 to T many.
times to power
Oh, yes. Yeah, W to the T.
So yeah, so I'll go over this topic again slowly. I think Bruno understood it. I'm not sure about else. Yeah. So I will go over it slowly. Yeah. Yeah. So what I'm trying to do here, so I'm trying to bound the pre-image of given node according to this map. Right. So my claim is that so given P of rho and the subset in this format, you can decode. Yeah, nobody should state claims like this. How are you going to do this? You take P of rho. P of rho looks like rho extended with a bunch of sigma 1, sigma 2, and so on. Yeah. So you know that even if you extend rho composed with sigma 1 with further sigma 2 and sigma n, this fact doesn't change. Something which becomes 0 still remains 0. Right. So how will you discover the first clause CL1? You just take your P of rho and then scan from left to right and see which of the first clause which becomes 0. That will give you the location of CL1. Once you have the location of CL1, okay, there are only W literals there. And using this T1 log W bits, you are going to point at which of these literals are those. And this pi1 is just look at the first T1 bits of the string, and that is going to give you pi1. So far, you have recovered T1 variables. So once you know variables in Q1, Q2, and QR, just peel them off and you get those given. So this is the worst case bound, and this shows that the pre-image of any point here is upper bounded by QW part. And that with that, you would get the quantity you are interested, which is probability of band. So the upper bounded by let's say P is less than half.
So you get your fine.
It is always less than what last time. And Hastad gets optimum numbers.
Depends on W.
Sorry.
P is smaller.
So if P is less than half, 1 minus P is greater than half, and 1 by 1 minus P is less than half.
No, but if P is less, I mean, you can get a 5 if P is small enough, right?
Yeah.
So second one is it should be smaller than something from W. W is much more.
So which should be smaller than W?
If W, okay, say P is quantified by compounded, but W is rather large.
It's not saying.
Oh, yeah, you're saying P is less than that.
Yeah. So note that original statement we are trying to prove, which is the bound on if P is greater than 1 by W, there is 1, which is always yeah. Yeah, so that concludes Prahladh's group. So yeah, let's pause for a moment and then continue with Rossman's group. I mean, meanwhile, if you have any questions or something.
Like I follow the code and the encoding, but I don't know why this encoding proof relates to computation or what you would generally think of as a proof of wisdom.
Yeah. Someone asked, gives you the statement after you prove it, why would I don't think of this as the root? Again, going back to the question that Bruno asked last time, why would Hastad have thought about this conditional using downward closure and so on? This is not the original proof, what we are looking at. It's a distillation of a previous proof. And this looks nice, but doesn't have any intuition. The previous proofs are ugly, but full of intuition.
Like the zero paths, they have nothing to do with actually making the computation as zero paths. We just use them as, oh, here's a placeholder that we can use for encoding. I expect the zero paths to face normal like computation sense, but I can't see the link. It makes no sense. It's
Okay.
very weak connection.
No, I mean, see, what we're looking at is for DNS, we're going to construct in the next talk, next week. So we're going to construct canonical relationship tree for an anti-formula at one go.
Okay.
That is, yeah, going to be.
It'll be an encoding argument, but
It is not quite an encoding argument, but it will be nice to know an encoding for that. But yeah, it's not a.
when you said what you're doing what in the next one?
So this is for DNS.
Yeah.
So this shows that the criticality of DNS is W, which W DNS is W, order W. So our result shows that criticality of I haven't defined what criticality
Right,
You know, but what did you say about the relationships? You said next week you'll be doing something at one.
Yeah. So this is the canonical relation tree for a DNS.
Yeah.
So next week we'll be looking at how to construct canonical relation tree for a formula.
Oh, okay. I need it.
Yeah. So there I think things might get more clear. What is the role of the zero path?
Okay.
Yeah, I mean, yeah, it's still unsatisfactory. Like, there are a lot of Yeah, it seems like there is a conceptual connection which is lacking. Proof is there. Yeah. This guy, and it's like essentially we're trying to found the pre-image of a random guy. Yeah.
I guess you could make it an entropy argument by saying that you can, I mean, this specifies, yeah, twice. Because somehow the entropy should be small, no? Of the image of the bad guys.
Yeah, if you can say something like that, entropy of some guy is small. I mean, essentially, what this proof is doing is that saying entropy of some object is small, if you can say that, that would be a very satisfactory.
Would be what?
It would be a very satisfactory explanation of why this proof is small. You can pinpoint at the particular object and say, okay, this is the object whose entropy we are studying. Something. Fine. Okay. So today and the next lecture, we are going to look at several such, two more switching lemmas of this kind. So again, these are again bounds of this form. And
but you're saying the downward closed sets also come up on the next one.
Yeah. Downward closed set is the definition of downward closed set is because of the choice of, if you do induction, right? I think they are bound to, sure. So all these things, okay, suppose if you are interested in real transform, suppose even if your DNA, even Hastad's proof, if your DNA is of this, that is, see this. All the clauses have disjoint set of things. You don't need downward clauses.
You don't need.
It's only because maybe this clause and this clause share some variables.
So I'm kind of seeing like a parallel between this proof and Hastad, right? Because in Hastad you also go to the leftmost guy that hasn't been fixed to 1, right? And then what do? You fix.
No, you ask whether the first guy is becoming 1 or maybe if you open that and okay, it's an inductive group. There are two cases we look at. One case is okay, what happens if the first guy is the one which becomes that is one case. First guy, what happens if first guy is not that group? That is one case. The other case is okay. C1 is set to 1.
That's the easy case.
Let's look at what happens to C2.
Right. Right, the easy case. So
yeah, this is taking care of.
It's not. If it's one by version, it will fall, so then you consider the
Sorry. Yes.
right.
At this point, you pray.
Yeah.
So, the decision coming out of that does look similar.
Yeah. If this is not the case, you query C1. Right. And if C1 is at least 1, C1 is set to 1, by the way, Then you have whether C2 is
So you look for the leftmost because
in some sense, this has the idea that you are going to the if you open the induction, you are going to the leftmost clause, which is not becoming 1, and picking up the variables from there, querying the decision there, and asking what about the rest. I mean, suppose S guys are picked up from this. What is the probability that the decision tree of the remaining guy is greater than T minus S? You can sort of think of this leftmost group as opening up Hastad's group. Let's continue. Right. We're done. So far, this is just a different group of what we've seen last time, the statement which we've seen last time. So now let's look at a different lemma.
Are we doing the other case one?
Let me state the lemma and then start from continuing.
Did you get something thank you or what?
These are not comparable. We try to see the this is the best. Looks like how we don't have a bound of control on the bottom values. Bits.
I think that's why I think perfect. Because one is around the criticality of Boolean formulas and the other is just
So in the previous setting, top pattern would be arbitrary, but bottom bits are bounded. Here the top pattern is bounded, bottom bits are arbitrary. And at this point, I will stop doing this. Some constant. Let's say it's true. Everything is same except for the W, we have a log n in contrast to the previous statement.
Okay. So you're going to show that this average is the one
So this again follows the same framework. Stay here. Now we're going to do an average case argument. So I'm trying some new presentation which I haven't done before when you were presenting it. So yeah, so just please be patient. I might be, yeah. So yeah, so let's look at this. So now you have a row, right? And we are trying to see its linear or differential. So I think from now on, so let's look at this. Okay, so how are you going to? Here is a way of recovering the pre-image of this guy according to. So Rossman is going to tell you in N. And
the first clause that's been set to 0.
Yeah, this is the first clause that has been set. So, and for each choice of Q1 and Phi1, and these two are different as the second choice. Okay. So again, there is another simplifying assumption which I haven't mentioned, which is previously we said instead of saying instead of looking at the property that the decision leader is instead of looking at this quantity, it's enough to be fixed.
Yeah.
Now let's make another further simplifying assumption. Fix a partition of T. So I don't know what R is. I don't know what you want to do R is. The partition is just partition of these how many such partitions are there?
So you can union bound over these partitions also.
Right. So how many such partitions are there? So you have these T matrix or whatever. How many ways can you?
But
So each way of picking a gap remaining the window is a partition. Each subset of these gaps is a partition. For example, one partition would be
right. T choose R, T plus 1 to R. T plus R to R.
yeah, some over R.
Huh?
Some over R. No,
R is not fixed.
R is not. So I'm saying, my case is you have this T matrix over there, and you're trying to select a subset of these gaps. For each selection of the subset of these gaps, that induces the partition.
Right, but is T to the T a good bound for you?
T to the T is not
Not good for you. Okay.
yeah. So we have T plus 1 gaps. Any subset of these, for example, this is the partition. This way of choosing.
There's no empty. None of our TIs are empty.
Sorry?
No construction of none of our TIs are empty. None of the TIs are 0.
Okay. None of the PIs are.
Yeah.
But we keep the number of this thing that then it will be none of Asian just start and then
Yeah. You can sum that and then you can see them.
Sorry, I'm not understanding. How do you encode?
you can keep the number of mistake as what
The number R is? Is that you? The 6?
No, if you
R.
how many ways are there to partition it into R sets? I mean,
Go into R sets.
so
Okay, so I see R to the T.
T plus R.
T plus R to the Those
Yeah,
samples,
it
one
is
to three are-
yeah.
So if you sum it from R goes from 0 to 1 to 3, that's correct.
No,
Or that'll be too big.
anyway, this is not spending this much time. Again, it's a nice combinatorial exercise.
You're fixed on the structure, right? So then you union bound.
Yeah. So my claim is that there are these many.
Perhaps you should start with where R is not greater than 0. Right.
No, but it can't, right? Because if that's the real number, then just when R is t by 2, that's already like t to the t.
Yeah, but this is not right because when R is equal to 3, there should be only one way to do it.
No, but this is something else. I mean, that's the number, right? People start to line.
I'm not sure. Maybe without
So it's like, you have say you have t boxes, right?
yeah.
Now add r boxes where you put or r minus 1. It's t plus r minus 1 choose r minus 1. That's the exact number.
But I think that's allowing for like empty parts.
Yeah, that's a
That's not.
Oh, okay. Oh no, that's not for him. Then that might just isn't that then t choose r actually? Right. Because you have t boxes, you replace the r guys.
There's symbolizing end of set point, end of
including this box.
Yeah.
yeah.
So then it choose r.
Yeah, it's probably there's no need to put something in the beginning. Yeah, you probably need only t.
Oh, nice.
Yeah, that's right. Because I'll be an except yeah. Yeah. So there is features are and it's not about yes, if you just did this thing right now, the special box is tell you the end of the sets. You don't need to restrict the R. You can follow R at once.
Yeah, so there are only three particles ways of partitioning this T into into things. And you could fix the worst partition and then work with that. And that will give you a factor of 2 power T. I mean, whose constants are we saving? We are dropping a lot of constants anyway.
Okay.
Yeah, so another simplifying dimension is you could impose more structure on the long path. So previously said the path is long if it's of length greater than t. Now then we said okay, it's long if it's exactly t. Now we are saying it's long if it has this nice structure, can be broken into R parts. First part is of length t1, second part is t2.
Okay.
Yeah, so now let's fix R and put into PR. We know that is not going to change anything in terms of not change much. Okay. Right. So suppose we have started with the row prime, which is in the image, the bias. Okay, row prime immediately will tell you L1. Okay. And now you have some non-moderate mixture. Okay, you have choice. Maybe potentially each subset would have resulted in a different group. Each subset and
Now I guess. Okay, so how are you going to encode Q1? Okay. Just a matter of two.
no, for each subset of the variables in L1 and an assignment with these variables, there is potentially an F2
Yes.
Okay.
And you say you're taking an average choice of this because that's how you choose.
Okay. So for a particular row prime, the pre-image of it is just the number of gates in the string.
In the tree, you need what? No, sorry. Say again.
So for a given row prime, for each row prime, you're constructing a tree.
So there you follow Taiwan.
Yes, this is fine. If you follow Q1 and Pi1, maybe you would have
Because these TI links, right, they depend on the specific Pi1, Pi2, etc. that you choose, right? Right, because for different choices of Pi1, you could be querying different clauses, which would have different number of variables.
Yeah, but I'm importing the structure.
So you're putting a structure on the path that was chosen there.
Yeah, if it's still a bad path, but it doesn't have the structure, I don't.
Okay, so let me try and understand what phi is now. So I'm giving you for free the formula. I'm giving you for free no, only the formula, right? The formula. And I'm giving you for free this RT1 TR numbers. And now the assumption is that there is a row. Okay, so there's a row that I maybe want to decode from row prime, right? And this row and this row. So I'm going to want to decode this row from row prime and from a path in this canonical decision tree where the lengths are T1 up to TR. And okay, corresponding to this path, I have some sigma 1, sigma r. And what I actually get to see is row prime. So row composed with sigma 1, sigma r. I get to see these values r T1 up to TR for this particular path that I have some canonical way of fixing. Maybe it's the leftmost path. It's in the tree, right? In the canonical decision. I get to see it. And that's it, right? And then you're going to give me something else, right? Some which you haven't really specified how to encode it, right? But and what you want to tell me is that on average.
Yeah, my first line is like the pre-image of row prime.
Yes.
Okay, is the size of this tree. I mean, is the construction of this tree clear?
No.
Okay. So the nodes.
Okay.
This, yeah, added to this.
All right. Okay, so there's the first node in the tree.
Yeah.
Okay, continue. Yes.
Okay. Yeah, the nodes are labeled by the indices of these two.
Okay.
So yeah, for example, if the first yeah, how would you recover? What is the algorithm for recovering row from row prime?
Yes.
Okay, so row prime will tell you what element is
Rho prime will tell you what L1 is because it's the leftmost thing that has been set to 0.
Right.
Now you know L1. Good.
Yeah.
Yes.
If someone tells me what subset and assignment.
Oh, you haven't told me how someone will tell me what the subset. Okay. Someone will somehow tell me Q1 and Chi1. Right?
For each such choice, I will potentially get an N2.
You will potentially get indeed. So for each such choice, you're saying that when I run this path from root to leaf, I'm going to get exactly one of the images row, right. 3 images row of rho prime. Okay. And yes, and how do I get that? Well, I figure out what L1 is, and someone will tell me which Q1, Chi1 I should follow. And that will allow me to know what L2 is. And someone will tell me, some other part of the encoding will tell me what is that?
No, it is just saying that L2 is a function of rho prime, Chi1 and Q1 and Chi1.
Yes.
Because, yeah.
Right, I can tell that.
Yeah.
Right. Yes, I know this.
I'm just trying to see that.
Oh, that's L2, right? Okay, so but now once I know L2, right?
Yeah. If someone
will tell me Q2, Pi2, and so on.
You would go on to discover the next.
And let's see. Okay, so you're claiming that these are the pre-images of rho prime.
Each leaf there corresponds to a pre-image.
Meaning that each leaf corresponds to one pre-image, and they're all different. And all pre-images are different. Okay. Yes, they have to be different, right? Because pi i's are different. The pi i's are different. Whereas the QIs are the same at each level. Is that true? Why? I mean, certainly it's an upper bound. The number of leaves in this tree is an upper bound.
Yeah. There could be leaves which are.
There could be leaves which are actually the same row. Or not. Oh, maybe not the same. Yeah. Well, no, maybe not the same.
Yeah.
No, because I see. Because for any 2 rows, there's a point where they diverge, and when they diverge, they have different variables for the different rows. I see. Okay, so I agree that. Okay, so I agree that there's as many pre-images as the number of leaves, and you're saying there's no more. Because given row and given a path in this tree, I can cover row.
Yeah, sorry. I mean, maybe 2 such things result in the same. That's not a problem.
No, but they don't.
They won't. Okay.
Because if you have two paths on the street, they diverge at some node. At the node where they diverge, they have the same setting of variables up to them, and then at that node, it's 2 different settings of the QI at that node. Isn't that correct? It's a 1-to-1 match.
Right.
That's right. So take any two leaves, they diverge at some node. At the first node, the only node where they diverge, these variables QI, let's say, have been set to 2 different things. Pi I for the first guy, pi I for the second guy. So these 2 different rows are different in these variables. What could happen is that on other variables that also appear in the tree, they end up being the same, but it doesn't matter because they're certainly different details. So I actually think that, and vice versa, if I actually have row in my hands, I can figure out which path in the street, I can compute rho prime, I can figure out which path in the street it takes, right? Because if I look at row, I find this leftmost path of length C1 up to T, right? And along this path, I remember the pi 1 that I took. So it's a 1-to-1 map. So these leaves, the leaves of this tree are exactly the 3 images of rho prime. Is that good?
Yeah. Okay. Anyway, so it's given any rho prime, you can construct this imaginary tree.
Okay.
Right. And the worst case bound essentially said that, okay, the ToC family is always bounded by W part T. The next guy is bounded by W part T. So the size of this tree is bounded by W part T1 plus T2 plus T2.
That's what the about.
That's what the worst case bound is. Or 2W part T.
Yeah, fine.
And W choose T1. Okay, W is the bottom vertex. No, I'm trying to say
What we did in the West.
in the worst case bound, what we did was essentially saying that when there also we are trying to find bound the size of this tree, but we have bounds on panels of this. Okay, so yeah, so yeah, so the way we are going to bound size of this tree is
Is it this thing where, with high probability, the width has decreased or something, right? Is that true?
with the water.
Yeah, with high probability of a row, right? The width is shrunk. Isn't that true? Right, and it has shrunk until it is like log n, actually.
Yeah, maybe we can probably say that.
Isn't that right? Right, because you're choosing row, right? And so okay, so oh no, but maybe it's not high enough.
Yeah, it's not high enough. I mean, last time what we did, we said in the case of AC0 formulas or AC0 circuits, we set a random restriction which is 1 by 100, and we ensure that bottom levels are all log s.
Yeah.
But that only happens with probability 1 by s square or 1 by column limits. Okay. So, okay, what is the bound on this? Here is a very simple bound. Find an L1 star to LR star. Okay. Which maximize the product of finance. What do I mean by that?
Which maximizes what? The product.
Yeah, so let's say D of L1 is the degree of this node, is the number of children of this node. We are interested in this right here. L1 star to LR star is that choice of nodes in this tree which maximize the product of its children.
I see. So you go for every path from root to leaf, and for each path you do the product of the degrees, and then you're trying to find the maximum path. Yeah. Okay.
Right? If you found such a L1 star to LR star, this is the guy which maximizes this quantity. D I defined on the fly. D of this is the degree of this L1. Okay.
But it has to be a valid path on the tree, right?
Yes.
I can't take like things that don't follow that. Because otherwise, so I don't understand. This is not just the product of the maximum degree at each level. It could be less, it could be significantly less,
Ah, okay. You're saying I could significantly less.
right? Because I'm forced to, you know, if I try more here,
Right. This is kind of adaptive.
yeah, it's a kind of adaptive version.
If I start.
Yes, there is
Where L1, LR are is a valid path in the So you go over every root to leaf path, and for each root to leaf path, you do the product of the degree for all that path. And the L1, LR star is the path that maximizes.
What do you want to say?
no, I'm trying to count the size of this tree.
I'm just trying to say that the size of the tree is at most the product of the DLI side.
Yeah.
Is that true?
Yeah.
Why is that true? Actually, it's trying to do.
The tree. That's called yes. Huh? Okay. Whatever it is. That's math therapy. Yes, I it's sorry. Oh, yeah. Why is that? Yeah.
So DL1 again? Okay, just a degree.
Yeah. First step is, I mean, you can probably do it by induction. Okay, let's assume that the size of this guy is upper bounded by such quantity for each one. This for each of these subtrees.
And then this is the number bound for the number of leaves. That like the
Yeah, I can put the upper bound on the number of leaves.
So DL1 star isn't actually dependent on the path, right? For L1. Like DL1 star is always B, just the degree of it. Is that right?
Yeah. L1 started off with L1.
Oh yeah, yes.
L1 started
Great knowledge.
with
So that's what would help with the induction, I guess. But you're basically taking the maximum of the children and multiplying it with the degree at L1, which is going to be right.
So for this particular tree, I mean, this is a statement about trees in general. Right? You have a tree, given tree, and you want to upper bound the size of the tree. Yeah. So we're interested in this particular tree. So what is DL1? It's let's say DL1 is the set of variables in the class DL1. DL1 would be that's minus 0.25. The subset of variables which you would have queried in L2, those couldn't have been variables from L1. So if L1 to LR are the variables, are the nodes in a path, this product is just going to be which is just probably equal to.
No, you still have to say which go where, right?
No, this is the identity. This case.
Oh no, because see there, no,
This is the connectivity of this phenomenon.
that's an at most.
Isn't it? That's probably it's also. Yeah, this is the atmost. This is the atmost. Yeah, not equal. This is not equal.
No, I think you define more things, right? You tell me, oh, maybe not. Oh, okay. Wait, what?
No, this is just the A1 to B1 and A2 to B2 is the A1 plus A2. And it's more generalized. That's all I'm saying.
Yes.
Right. Right. Yeah, this is just right. Yeah, at the end of all this, how I said the size of this tree is upper bounded by this number. Take the union of variables appearing in
Times 2 because there's a pi, no? Times 2
sorry, yeah, there's a kind yeah, so for a particular row prime, right? You pick these Li stars, right? I'm not telling you how to pick them, but it's not experiment. And in terms of the Li stars, this is the upper bound on it for a particular row prime. So again, there's a correspondence between row primes and these Li stars. Okay. So
we want to show that on average, this is a small number.
right.
On average over the choice row prime.
Right. So let me use this part of the board. what we're interested in is sum of all the time.
Yes.
And we said this pre-image is upper bounded by the size of such a tree.
It actually equals.
Exactly, it means size of the tree. And along the process, we also define its correspondence. Given a row prime, we are producing the R integers. Right? Let's call this map.
Maybe side.
All from side. Right?
Right. So give me row prime. I give you row prime. You compute these out on star. But you're the path and largest degree.
Right.
And
right. Yeah, in terms of L1 star to L star, we have a bound on size of the cell. So the natural thing is to right, club all row primes. You have a bunch of row primes, right? Right. Collect the row primes whose image according to size given element given tuple of R and D.
You're saying that if you clump them all by the choice of Li,
right?
Is that it?
Yeah, and then do this summation.
Okay, you're saying there's not so many Li?
So in other way, this summation is exactly you pick a bounded by you pick an arbitrary choice of the bounded by and ask and look at this sign inverse element to L. Right. That is the number of for each of these guys, that number is fixed. For any row prime in this partition, that number is
so it only depends on the choice of clauses. Right, I choose the first clause. Yes. Nor into Zentina, it's fine.
and times what is your
Amar? Oh, of having a one alarm as
Right.
being the right guy.
right. Yeah. Now, in fact, here, we don't have. Right. Yeah, so my thing is, yeah. Let's pass the statement first and then
Right? Basically, the odd maps.
not this need not fine. This probably is true. Yeah, psi is taking our marks. Yeah.
Oh, okay. But L1 to LR is for any L1 to LR.
Yeah, so for fixed driver,
Yeah.
L1 to LR, what is the probability that psi rho prime is this L1 to LR? Again, this is upper one. In order for psi rho prime to be equal to L1 to LR, a lot of things have to happen. And one among them is that rho prime sets all letters in clause CL1 to zeros. And that is the only property that one. This event captures a lot of things.
Sure.
One among them is that rho prime in particular sets all the variables in L1 to all the literals in L1 to zeros.
Okay. But that's tiny, right? That's even smaller than like rho, what 1 minus rho, 1 minus p over 2 to the power of this.
But it's possible. P is small, that's fine.
Yeah, that's smaller, right? That's smaller. There's 1 minus p.
P is bigger than a half, if we're assuming that's less than.
Yeah, 1 minus p is always less than 1. This problem.
Sure. No, let's say P is bigger than 4, right? Somehow need that. Fine. What? Right, no?
P is always less than
P is bigger than 4. No. P is bigger than 3/4, is what I mean.
Okay.
Is that something or something?
Why?
Sorry, you want 1 minus P over 2. At 1 minus P over 2, you want it to be less than.
That's always true. This is always less than 1.
Oh, I see.
Oh, yes. Okay.
Oh, I see.
Right?
All right.
Okay. So what do we have? What is the expression we have at the end of all this? We have this really nice expression. I'm just going to talk about it very crudely. And we just left with we are just left with the performance from at the end of this. So yeah, again, this is something which I came up with today. This is not the way it's written or the way it's, but yeah, this avoids a lot of symbol pushing and this. This is the symbol pushing. Yeah.
What's symbol pushing?
Just mindlessly writing symbols and then moving here and there and then all other things.
Right.
Yeah, that's how the proofs are. Yeah, the actual bit. But yeah.
So okay, so now you're saying
So
let's start overall one more.
Does this remind you of something which you must have seen, which you've seen in the information daily class? This is minus p log b summation or minus pi log b. Sorry. Okay, now we are left with bounding this guy. Okay, maybe I jumped around a little bit. The actual thing is this expression, right? And furthermore, we know that this element of LR are a partition of the space where rows are coming from. So these properties when summed over L1 to LR is upper bounded by 1. So in fact, these numbers when summed over L1 to LR also is upper bounded by 1. So you can think of this as a probability distribution. And this is upper bounded by log of the support, which is
if you think of that as a probability distribution, then this is like the expected value of t times log of the probability. Like,
so yeah, okay, maybe I am just take it very loosely. This is just one convex set.
sure. But the t should come up, right?
Yeah, this is not, sorry, my bad. This is not minus p log pi. This is minus p log pi part t. So, still.
Oh, yeah. But yeah. Okay. And you're saying convexity is still.
Sorry, I'm okay. So you're saying it's what?
Yeah, the common way of doing this is writing this as log 2 power okay. And when you push this summation 1 by 2 inside, it just becomes
Oh, I see. Because you're just saying it's convex. think it's conquered. It's conquered. What? Because you're saying.
What is going in the right direction?
Okay. Okay. So, so let's see. So you're saying that the average of this value. So your f is log of the
Yeah, continuity of log.
cavity log.
Log part.
Log party. Cavity log party. Right. So the average value is less than the value at the average, and the value at the average turns out to be the number of L1 LR. The party. Okay. All right. So.
Yeah, so in between, I think I was a bit loose. So I dropped the 1 by T party factor.
What?
This V Li by T is upper bounded by VLI whole power T for sure, but you could put a stronger bound. And you're saying n choose R is upper bounded by E n power R for sure, but it is also upper bounded by En by R whole power.
I always forget it. Okay.
Yes, because n choose R that 1 by T party is going to come to rescue and kill this R.
So what? So now it's too confusing for me.
Sorry, this is just a calculation which I probably did very background. So, yeah.
But can you write it in big symbols?
Yeah. I'll start from here and go over it again.
Okay. Yes.
So I think at this point I can get rid of this.
Okay.
Yeah, so what we left with is function along the log.
You're ignoring the e to the power.
Yeah, and I'll just not write the part.
Easy part.
Yeah, and this. Yeah, this is what we have. So, right? Yeah, this is something which appears in the subsequent paper as well. I mean, what? The subsequent paper, our paper as well, and the previous one. This paper, then Rossman's regular thing, and then
Unity. Sorry, I'm not talking about.
sorry, this particular trick of writing this convexity. I mean, this probably the reason why it's called the entropic switching lemma.
Oh.
And yeah, so you would write this as log
Where is divided by T? The divided by T. Yeah, but on.
It's actually this guy.
Oh, really?
Yeah. I was.
Now you use convexity. Is that right?
Right. So let's pull on the contact part of the oxide and it's move there. Sorry. Yeah. And here I'm usually using that sum of L1 to L1. That is fine. I could have used the convexity. This is what I want.
It's not actually this.
Because 3.
Yeah, why is that true? Why does that statement hold? Because of this.
No, that's the probability is less than that.
Okay. My bad. Maybe I have something too early. Yeah, so maybe we don't do this yet.
You keep it problem.
You keep this as still this probability
So that's taken
till you use convexity and finally use. Let's see. L1 to L1. What we have is so we know that
Now
y, yeah.
what? No, now it equals 1, right?
Now it equals.
I mean, now it's just the sum of probabilities of some events.
Yeah.
So it equals 1.
Now you use convexity.
Comparative.
So comparative law part. You get
Over times the it's all of the sum of the now you use the fact that here
now we use that.
and you get K and you get 1 over T to the power T times log of the number of L's. And the number of L's is at most M2 log. Why is that?
Yeah, so L1 has n possibilities, L2 has n possibilities.
Oh, I see. Yeah, sure. And okay.
And this is and R is always less than T because R is the number of partitions.
So, okay. That's your log into the T.
Yeah. That is number one on the Now that you've seen this, let me give the formal and cleaner proof of this, and which is our next proof is going to follow that. I mean, I'm not going to open up the next proof like this. I don't know how to do that. I'll try to see. Yeah, let's just see a cleaner way of doing this thing.
Okay, which one?
The same thing. I mean,
With the same sentence.
with the same thing.
And then at the bottom.
Maybe we do that next time.
Okay.
Because then we get to warm up with something we've already seen.
Yeah.
And before we go into the big one. Okay. All right. Anything you want to say prepare us for next seminar?
Okay. So, yeah. So, what is coming ahead? What next? What are we going to look at? So, yeah, the story of this criticality is first there was a proof that parity not is zero. Then someone asked, okay, AC0 circuits cannot compute parity, but can they approximate parity? And Hastad in 2014 comes and shows, he comes up with a multi-switching lemma and shows that parity cannot be approximated by AC0 circuits as well. And that's the correlation bound. Okay, there was the circuits, there was a low worst case lower bound and then average case lower bound. And then independently Rossman for formula showed a lower bound. In probably around that time, 2017. Yeah. And the question in the open is that what is the correlation for of parity with formulas?
With small formulas.
With small formulas. And yeah, that is a sequence in which the first thing is you have switching lemma which came out and showed that showed the lower bound. Then there was multi-switching lemma, which is a clever way of avoiding union bound. If you solve, I mean, if you call the lower bound, you are doing S union bounds as an effective. First case. I mean, we're switching.
Yeah.
And we're potentially applying switching lemma S times.
Well, I mean, for constant depth circuits, it would be D times. But you're saying now that
No, for each layer, we are applying it to each of the DNF.
Oh, yes. Oh, I see this.
So essentially, we are applying switching lemma S times, and so we are doing a union bound on S objects. So that's bad.
Okay.
So multi-switching lemma is something which is a clever way of not doing union bound.
I see. So like you directly prove that if you have S many DNFs or something, then they all collapse with probability, right? Something like this?
Yeah.
Okay.
So they try to construct suppose you are given k DNFs, you're trying to construct a common decision tree. That's not the switching lemma. Then there was this top-down approach of Rossman in doing formula lower bounds. I mean, okay. This is the title of the paper is something to do with average sensitivity, but it's in some ToC 17. This is worst case lower bound for formulas.
Okay.
That again.
Why do you call it top down?
Top down. Again, I need to, maybe I don't have a very good justification, but okay, but I'll still try it. So, okay, if you look at the AC0 circuit code, what you're doing is you're first applying it to the bottom level DNFs. Yeah, it is still a restriction based proof. It is using Hastad switching lemma. But the parameters with which you apply switching lemma are defined in a top-down manner.
Well, okay. For me, top-down proof is something where, you know, like you give me, there's the communication, formulas from the top down or communication protocols, and games. So top-down proof has to give me an adversary, right? I tell you what Alice communicates, and the adversary has to go left or go right, or something like that. I don't know if that follows from that proof, but if it does, I'd be very surprised and interested in that.
The parameters, it might not be like a deterministic adversary, but the parameters are in some sense acting adversary to make the function.
The question, you can always come up with parameters that allow you to do this. The thing is that you can't, it's not easy to compute them like in moment time inside of the system. So, you know, so the parameter would be, you know, Alice divides into 2, and the adversary goes to say the size that has more depth. Left, right? So you can know the question is you can compute this. But there's, there's this whole talk of top-down lower bounds. And from my understanding of what it would mean this, right? So, you know, you have your communication matrix of your partial matrix in the game, and then Alice communicates. And then the adversary immediately, before seeing what else Alice is going to do, has to decide left or right. And he has to survive, you know, like as much depth. Right, or you know, if you want size, then what the adversary does is a little different. It tries to, it goes left with some probability and goes right with some other probability. And then the entropy of what you get is the size. So I understand that you use the top-down lower bound word very innocently, and I'm like, I thought a lot about this in particular term. But it could be, because I haven't read Rossman's paper, so it could be.
No, that I think, okay, the paper, okay, it's a formula lower bound. So the way it uses is, it defines random variables. Okay, this P with which we are applying switching lemma, that is a random variable.
Okay.
So, going back to what you were saying, maybe if you are, are you allowed to use randomness in a top-down thing? In your, for you, top-down is a communication protocol.
But does he need to know, for the choice of P, does he need to know the size of the subpoint, the left and right subpoint? Is the question.
Yes.
He does, right? So I would expect that. But that already means that it's not,
you already seen the formula.
You've already seen the formula before.
You know what it says.
Exactly. So somehow, somehow, you know, so if you already could compute the formula by some polynomial time algorithm, you could prove a lower bound just by running the algorithm on the formula, right? So somehow it proves the lower bound. Am I wrong?
Sorry,
no, sorry. This is actually a little different. It's a little different. Right, you've already seen the entire form. Exactly. That's the point. Yeah. That makes it.
Yeah, all you're asking, tell me the size of this. I'll give you a restriction. I'll sample a restriction for it, such that it becomes a small restriction.
Okay. Oh, and it only. Oh, but that might make a difference. it's interesting whether it's top-down or so because you're telling me, you know, in the end, I want an explicit lower bound prover. And for me that means it's an this object which exists by definition, which is that you know, Alice communicates, and let's say you just want to prove a depth order, right? Then the lower bound prover comes and says, go to the 0 side and go to the 1 side. And the lower bound prover loses when he falls into a monochromatic rectangle. So the number of rounds for which the lower bound prover can win is exactly the depth of the front or the depth of the protocol. Right? And so for me, a top-down lower bound is you give me an explicit algorithm that tells the prover what to do. And at some point, so I'm not sure if these things actually exist.
Okay, yeah, maybe that word is loosely fine. Right. Generally, I think restriction-based methods are all bottom up.
Right. Yes.
It's just that.
That's my preference. Yeah. All right. So we're done?
Yeah. Yes.